I don't wanna grow up, I'm a curious kid. The world has 100 questions I can play with. So I'll open my arms and eyes and wonder every day till the day I die. No one really knows why gravity exists.
Welcome to Ask a Science Envoy, Spider, Love, and Dark Matter, presented by Wonderfest and by the Berkeley Public Library. I'm Tucker Hyatt, founding director of Wonderfest, the Bay Area beacon of science. Here to tell us about the Berkeley Library, perhaps just a bit, is librarian Will Marston.
Greetings, everyone. I'm delighted to be here at this event with you. Just wanted to mention that STEM programming in the library has just increased in importance for us, and we are so delighted to have Wonderfest as being part of that. At Berkeley Public Library, we now have 4 telescopes that we loan out. We have binoculars, and I put out a weekly sky report, and this is just more programming for STEM research that is very important to the library. So delighted to have you here. Thank you.
Great, thanks, Will. Here comes our first speaker. Stanford physicist Joe Singh will help us explore the dark side of the universe. Joe is a 4th-year PhD student at Stanford, working to understand dark matter with physics professor Kent Irwin. Joe earned his undergrad degree at UC Berkeley. Recently, Joe was awarded a highly selective Quad Fellowship, an honor presented jointly by the governments of Australia, India, Japan, and the United States. Please welcome Stanford's emissary from the dark side, Joe Singh.
Thanks so much, Tucker, for that introduction. Thank you, everyone, for coming today and I'm going to be talking to you all a little bit about the dark side of the universe and what we know about it and what it means. So before I talk about what the dark side of the universe is, let me give you all a brief tour of the universe as we know it today. So this beautiful picture is from the James Webb Space Telescope, which was launched in Christmas 2021, and it's sitting in space right now in orbit, giving us all these beautiful pictures of the universe free from light pollution, atmospheric noise, etc., etc. So we get these pristine, beautiful pictures out from deep space. And you know, when we look out at the universe, we know that it's really big, but just to give you a sense of how big it is, we think that there's roughly 1 trillion galaxies, and take this number with a huge grain of salt. It could be 2 trillion or whatever. It's just a large number. And roughly there's about 100 billion stars in a galaxy. So in our Milky Way, there's about 100 billion stars. And if you multiply those numbers together, you end up getting that there's 10 to the power of 23 stars in the universe. This number is 1 followed by 23 zeros, which would just take up the entire slide. So, but you know, I still want to give you a sense of how colossal this number is. So if you think about, let's come back from the universe back down to Earth, 10 to the 23 stars in the universe. And just to give you a sense of how astronomically large this number is, pun fully intended, think about all of the water on the Earth, all of the water in the oceans, all of the water in the skies, in the atmosphere, just anywhere you can think of, right? And a huge amount of water. And now think of all the tiny, tiny water molecules that are in those oceans, in the atmosphere, in your body, in all the lakes. That number of molecules is about 100 times smaller than the number of stars in the universe. That's about 10 to the power of 21. So there is really just so many stars out there. And think about that, all these stars come with, like, you know, a couple of planets on the side. So there's really just a lot of stuff out there to think about. One of the most basic questions that you can ask, and it might appear like a silly question at first, but this is where it gets interesting actually, is, okay, there's a lot of stuff out there, but how much of the matter in the universe is actually galaxies, stars, planets, normal stuff that we understand and whose physics we know? And you might be tempted to guess, 100%. That's actually wrong, surprisingly. And maybe 75%? No, not even that. How about 50%? At least half, right? We've got to know about half of the universe. That's wrong also. It actually turns out that there's only 15% of the stuff. So think about it. All of that infinity of stars, that's just larger than the number of water molecules on the planet. That's only 15% of the universe. And that means that 85% of what's out there is invisible to us, and we don't have a full idea of how it works. And this invisible majority is what we call dark matter. And so this 85% of the universe is what I'm going to be talking to you more about today, and explaining to you what we think it is and how we're going about looking for it. So I just made a pretty bold claim to you to start off this presentation, which is that we don't understand 85% of the universe, which, as a physicist, is quite damning for my own field, because, we'd like to say that we know more than that. So, in the good scientific tradition, extraordinary claims require pretty strong evidence. So let me share with you some evidence about why we think that there's so much, that the stuff in the universe that we understand makes up such a small amount of it. And there's a lot of different pieces of evidence, but I think my favorite piece of evidence that I want to tell you about today comes from when we look at galaxies out in the universe, and specifically when we think about how galaxies rotate. So here's a picture of our nearest neighbor galaxy, the Andromeda galaxy. And just like our Milky Way, the Andromeda galaxy and any galaxy is basically just a collection of stars and other objects like planets held together under the force of gravity. And crucially for us, these objects in the galaxy orbit the galaxy center. It's exactly like how the Earth orbits the sun, which is the center of the solar system. Similarly, the stars in a galaxy orbit the center of the galaxy. So more precisely, what we're interested in exploring is so let's say you're a star sitting in a galaxy. How does the speed at which you move around the center change as you go really close to the center versus really further out? And this is what astronomers were focusing on throughout the 20th century. Kind of just, they wanted to make sure that they understood everything and that things moved as they thought they would. So also as good scientists, before I tell you what we found, let's try and understand the situation, and let's try and make a prediction about what we might expect to see when we make this measurement. So as I said before, because of gravity, the stars move in orbits around the center of the galaxy. So on the right, you can see a picture of our sun, and our sun also orbits around the center of the Milky Way. You can see, I don't know if you can see my cursor. I'm going to try use it as a pointer. But this yellow circle, it has a 230 million year orbit. That means it takes 230 million years to come back to where it starts. And its distance from the center of the galaxy is 28,000 light years. And for those who might not be familiar, a light year is a unit of, it's how we measure distances in space. And this technical definition is the distance light travels in a year. But to kind of really gain an appreciation for how huge this distance is, 1 light year is basically equal to if you ran around the equator of the Earth 200,000 times. So that distance is 1 light year. Or alternatively, the distance to the sun, which is about 100 million miles, is only about 10 light minutes. So think about how many minutes there are in a year and multiply 100 million miles by that, and you get how big 1 light year is. It's basically a huge number. Anyway, so our sun also orbits around the center of the galaxy, and as you might expect, if the force of gravity is stronger, then the stars will move faster. Just like if the force of the sun on our Earth was stronger, our Earth would move faster and our years would be shorter. And there's 2 main things that affect the strength of gravity. So one is the amount of mass in the core of galaxy, all the stars and dust, etc., that's exerting this gravitational force. And the more stuff there is, the stronger your force of gravity. And there's also the distance from the core. And the further away you are from the core, the weaker the force gets. And it falls off pretty fast, actually. So if you combine those two pieces of information, you get that the more mass there is in the galaxy, the more stars, etc., the faster a given star sitting outside near the edge somewhere should orbit. And then similarly, the further the star that you care about is from the center, the weaker the force of gravity, so the slower it'll move around. And so there's these two forces, these two factors, one speeding up the stars and one slowing down the stars. And so what scientists expected, given this gray dotted line you can see, actually, let me explain what the axes are in this plot. So this graph is basically what the scientists plotted when they measured how fast the stars rotated in the galaxy. So on the bottom axis, the horizontal axis, you have the distance from the center of the galaxy in the units of light years. So these are huge distances. And on the y-axis, you have the speed that they measured the stars moving with. And what you expect in this gray dotted line is that as you start going further from the center of the galaxy, because gravity gets weaker, your star speed should start decreasing. But as you see from the plot, what they actually found was totally unexpected. Not only was the speed higher than they expected, but it kept going up as you kept going further away from the center. And this came as a total shock, because this was something that we thought, we were just doing a sanity check, and it turns out that we get this completely unexpected result, which is kind of, how science works. So this, we were shocked that the star rotation speed stays high. And as I explained to you in the previous slide, that means that the force of gravity is stronger than we thought. And the only thing that can make that happen if there is more stuff hidden in the galaxy somewhere that we can't see. And so we must have this extra invisible mass for the extra gravitational force. And that was the first piece of evidence we had, that there is some dark matter hidden inside that we can't see. So that was just one piece of evidence. However, the crazy thing about dark matter is that there are plenty of other kind of different sources of evidence that all seem to point us to this weird conclusion. So one example is not just of single galaxies rotating, but of entire galaxy clusters. So a galaxy cluster is a group of many galaxies all bound together under gravity. And when galaxy clusters crash into each other, that's obviously a very interesting event that astronomers study a lot. And even studying those, they found evidence for dark matter. And my personal favorite piece of evidence, which I won't go into in the interest of time, comes from something called the cosmic microwave background, which you can just think of as the very first light in the universe that came about almost, as soon as it possibly could after the Big Bang, after the start of the universe. And so this picture at the back of these red blue spots is a picture of the cosmic microwave background, all of this light in the universe that we see coming from everywhere. And if you study it carefully, you can actually see the imprints of dark matter in here as well. So there's really evidence everywhere, from the scale of individual galaxies to the entire universe, that suggests that there is this invisible 85% out there that we just don't understand, and that we should really start thinking about. So now, hopefully, I've convinced you that dark matter is real, or there is something out there that we need to try explain and understand. So now I want to talk to you a little bit about our best ideas for what we think dark matter could be. So, how do we start piecing together this puzzle? This is the business of science. We have all our evidence. We need to try and make some sense of it and see what to think about next. So as I said, we're very sure that dark matter exists, and we can see its kind of gravitational effect out on galaxies, on the universe. But in terms of actually what it is, what, particles it might be made up of, what properties they might have, we have zero concrete idea. But we do have many, many, many theories that can explain all the astrophysical evidence. So here on the right is this wonderful chaotic mess of dark matter theories that people have come up with that all of them explain the evidence well. And so, as physicists, we now have to think about, okay, well, how do we test these theories with experiments? And, like use the scientific method to try understand what is the right answer here. And the sort of leading philosophy for physicists here has been that, okay, it's one thing if your theory solves dark matter. We definitely want that. But since there's so many theories out here, if the theory that you're proposing also solves a different problem from somewhere else in physics, then we're going to treat that more seriously, because ultimately the universe is one. These so ideally the perfect theory would explain everything. So if the theory of dark matter also happens to explain other things, then that's how we have chosen to prioritize where we start looking for first. So with that sort of philosophy in mind, the first candidate was called the first candidate theory was the theory of WIMPs, which I love the name. It unfortunately, when you say the full name out, it becomes less fun. It stands for weakly interacting massive particles, but of course we'll just continue calling them WIMPs because that's more fun. So WIMPs are a particle that's predicted by a theory called supersymmetry. And I won't go into the weeds of what supersymmetry is, but basically you can think of it as something that tries to explain the four fundamental forces of the universe, which I've shown in this picture here. So you have gravity and electromagnetism, which are ordinary everyday forces that people are very familiar with. And then there's these other two forces, which you don't see on a day-to-day basis, but they're really involved in things like nuclear reactions. So the strong force, for instance, is responsible for holding atoms together, and the weak force is responsible for a lot of radioactive reactions you might see in a nuclear power plant, for instance. Supersymmetry tried to explain all of them at once, and it just so happened that it, as a natural prediction, it created this new particle which had all the perfect properties to be dark matter. And this was so unexpected to physicists. We were so happy. This was called the WIMP miracle. We were so excited because you're trying to solve one problem, one huge problem in physics, and you get a solution to another problem. It was just too good to be true. And so the field immediately began looking for these new particles, and we began designing experiments. Here's a picture, for instance, on the bottom from one of such experiment, where you'd have the incoming particle being a WIMP, and there's this big detector, and if it hits something inside your detector, it would knock off particles called electrons, which you could then detect. And there's many such experiments like this, underground dark matter laboratories worldwide, ranging from here in the US down all the way to the South Pole. So because, the entire world was interested in, finding this dark matter, miraculous dark matter candidate. But, after 20 years, unfortunately, we haven't found anything yet. So I know this picture looks a little bit intimidating, but basically all you need to know is that this picture shows us what properties this dark matter particle could have. So on the x-axis, you have how heavy it is, and on the y-axis, you have how strongly it interacts with other things. And basically, if the region on this plot is shaded, that means someone has already looked there and they found nothing. And so you see that after 20 years, there's not a lot of white space left. So we've searched hard everywhere we could, and we didn't really find anything, which is, kind of sad. But it's leading people to say that the WIMP miracle hope for dark matter is now dead, which is a real shame, because supersymmetry was an absolutely beautiful theory But, as good scientists, we can't just think about beautiful theories. We have to go where the evidence leads us. So people are still continuing to search for WIMPs, but now we need to think about other possible solutions that might make up that vast 85% of the universe that we don't understand. So there's a second candidate dark matter particle that people are begun to focus on more, and this is called an axion. So like the WIMP, the axion was predicted as a solution to another physics mystery called the strong CP problem. And that has a bit of an intimidating name. I won't get into the nitty gritty of what the strong CP problem is, but it's just all you need to know is that it's a very deep problem regarding one of the four fundamental forces that I discussed before, the strong force that holds atoms together. So unlike supersymmetry, this isn't related to all the four forces of the universe, but it is a deep question about one of them. So it's still pretty, it's got pretty good motivation behind it. And most importantly for us, there's kind of like a little axion miracle as well, because like WIMPs, in the right circumstances, axions also have the property to be the dark matter that makes up 85% of the universe. And here's a fun fact for y'all. So axions were named by Nobel laureate Frank Wilczek after this dishwashing detergent. And he named it this because he was so happy that he found this solution because it cleaned up the solution to the strong CP problem. So if it turns out that axions are the dark matter, then 85% of the universe will be named after dishwashing liquid, which might be the most interesting trademark violation in the history of the universe. So, axion experiments, so the field of axions is much younger than the field of WIMPs, and axion experiments are ramping up all over the world. So here in the US, we have the axion dark matter experiment based at the University of Washington in Seattle. We also have the dark matter radio, which is the experiment that I work for. So in the left, you see my advisor and a couple of our senior scientists working on a prototype version of our first detector. And then here's me on the right, working on building the next generation of our detector in our lab here at Stanford. And another super cool thing about axion experiments is that they're also a very fun playground for next generation quantum technology. So you may have heard of things like quantum computers or quantum sensors in the news recently. It's become a little bit of a hot thing. So we play a lot with those types of things as well to try and make our search for axions even more sensitive. So for instance, there was a very cool experiment called the haystack experiment that just 1 year ago looked for dark matter with a very bizarre quantum thing called squeezed light. So I found that really cool, like looking for dark matter by squeezing light. So there's a lot of fun games that you can play when you're looking for axion dark matter that will obviously help you find dark matter sooner, but they will also have potential applications outside. For instance, people are thinking about using squeezed light in areas like MRI. So axions are gradually taking the torch from WIMPs, but we're still on the hunt for what dark matter could be. So just to conclude, the evidence is overwhelming, as I showed you, and I'm happy to talk more about the other examples that I brought up. We only understand 15% of the matter in the universe, and 85% is completely unknown to us beyond the fact that we know it must exist. And we have lots of theories for what dark matter could be, but of course, in the spirit of good science, we need to check that with what the universe is actually telling us and what the evidence supports and doesn't support. So while the WIMP miracle was an absolutely beautiful theory, it hasn't been supported by experiments so far. So we've switched to the next best thing, which are now axions. And there's lots of other things to explore as well. And I kind of want to leave you with the message that, if anything, dark matter shows that there's just so much left to discover about our universe. And so we need to absolutely keep on looking, because who knows how many more surprises are waiting out there. So with that, I will stop.
Wow, Joe, thank you very much. I have a feeling we're going to have some good questions. As they perhaps collect in the chat here, maybe I'll ask a couple. Also, I want to remind you that if you want to ask the question yourself, please just raise your hand. When recognized, unmute yourself and fire away yourself. All right, Joe, you just handed us the remarkable number of 85% of the material universe is this invisible dark matter. I got to think that means that 85% of our solar system is also dark matter. And if that's the case, why is it that it wasn't discovered earlier? You'd think that the laws, Newtonian gravitational laws that describe the orbits of the planets seems to work very well. We can predict the paths of the planets incredibly precisely. Do you know why it is that we didn't discover dark matter through just planetary observations?
Yeah, so that's a great question. So as it turns out, one of the other pieces of evidence for dark matter, which answers your question, is that dark matter has a huge role in what we call structure formation. So dark matter, for instance, is the main reason why galaxies form. And as part of that model, what the simulations show us is that dark matter, it doesn't exist uniformly throughout the universe. It mainly exists in what are called halos around galaxies. So the outer edge of a galaxy, we believe, is surrounded by a dark matter halo. And that's why, for instance, like all these dark matter experiments are actually called haloscopes, because we believe that dark matter mostly exists in the halo around the edge of the galaxy, and then it sometimes streams in. So there's not enough of an influence to affect, for instance, the orbit of Jupiter or whatever. But and that's why you need super sensitive detectors. But at the scale of galaxies, and that's why stars in the entire galaxy rotating, you can see the effects of the halo.
Great, Joe. Thank you.
Mm-hmm.
Douglas S. asks here, if dark matter had a large decay factor, in other words, I guess if it did disappear, turn into something else, Douglas says, I don't think we would have the large scale structure of the galaxy that we have. What do you think?
That's absolutely right. And that's why we don't think that dark matter should decay quickly. It should be fairly long-lived. Yeah, so absolutely, that's spot on.
Okay, thanks, Joe. Stuart asks, we'll get to that raised hands in just a minute. Stuart, you said your slide, Joe, mentions extra dimensions. What would be the objections to this theory? Can the evidence be the gravitational effects of matter which exists in other dimensions?
It totally could be. So let me say straight off the bat, I'm not a theorist, but I will do my best to answer your question. Yes, so people have proposed that gravity acts through extra dimensions or whatever, and it leaks out. And we can't definitively exclude that. It's very hard to test. Those theorists haven't proposed experiments for us to be able to test that. So we can't say no, but we can't say yes.
Okay.
Yeah.
Thanks for the question, Stuart. Jerome, your hand is up there. Please unmute yourself and make yourself visible if you like and ask your question.
Yeah, basically, I have two questions. The first question is, what happened to dark energy, number one? And number two, what do you think of the new equations of general relativity that have a scale factor that is actually able to predict the orbits accurately?
Okay, so first on dark energy, so you're absolutely right. I shoved dark energy under the rug in the interest of time, but it is in my backup. So what Jerome was pointing to is the fact that, so I hid actually most of the story from everyone here, because while what I said is true and that dark matter is 85% of the matter, actually, if you think about everything in the universe, the vast majority of it is this stuff called dark energy. If we don't think we have any idea about dark matter, we have even lesser idea about dark energy. But we know it's there because we can see its effects. For instance, There was Saul Perlmutter at Berkeley won a Nobel Prize in 2011 because he showed that the universe, people here might know that the universe is expanding. What he was able to show is that the universe is expanding, like its expansion is getting faster. And so we believe that dark energy is the reason behind that. But beyond that, there's a lot of question marks. So yeah, so yes, you're right. Dark energy is there. I didn't mention it specifically in the interest of time. And your second question was regarding like, you know, could you repeat your second question? Sorry.
I took his mic. Let's see. Maybe I can repeat it. Maybe I can't. Jerome, where are you there? Let's see. There he is.
Basically, I was asking about the modifications to the general theory of relativity that parameterizes the equations, like with a scale factor or something like that, that allows for a solution that works for galaxies.
Oh, right. So essentially you're asking about modified gravity, right?
Yeah.
Yeah. So that's another thing that I omitted in the interest of time, but Jerome is right again in that when we, when we go back to the galaxy rotation curve, one answer is that what I suggested, there's invisible stuff there. Another answer could be that the stuff that is there is what we see, and that it's our understanding of gravity is just incorrect at those large scales. And so those types of theories which try to modify our understanding of gravity, such as what Jerome is talking about, are called modified gravitational theories. My answer to that is that the consensus in the community is still that dark matter is probably the solution rather than modified gravity, because I don't think many modified gravity theories can explain the solution from the cosmic microwave background. These types of fluctuations that you see in the temperature of the cosmic microwave background come out beautifully as a consequence of the cold dark matter model. So while modified gravity can explain galaxy rotation curves well, I don't think it works with the CMB.
Thank you, Joe. And Jerome, thank you for such a tough question.
Thank you, Joe. That was nice.
We have time for one more question. Gary, please unmute yourself and fire away.
Okay, thank you. My question is, you said that the density of dark matter is not constant and it's concentrated around the halo of galaxies. Does that imply that looking for it on Earth is a futile effort? That it may just be so diffuse that it's almost impossible to find?
So it's not almost impossible, but it is very hard. And that's why, because dark matter is concentrated in the halos, but it'll still kind of flow through the galaxy. It's not restricted outside of the galaxy. So there will be a small amount that just is probably flowing through you right now. And that's the reason why, for instance, a lot of those dark matter experiments were underground. And for instance, in our Axion experiments, we need to use this next generation quantum technology because it's not impossible, but it's really hard. And you need to have a really, really good detector to have any hope of being able to see an actual dark matter signal.
Gary, thank you for the question. Joe, thank you for the answer. It's frightening to think of dark matter going through me right now. I imagine our next speaker is going to be talking about spiders in my house. And I want to assure everyone we'll have a chance to give Joe and both of our speakers, Trinity to come, a wild hand of applause at the end here. So again, Joe, thank you. Let me introduce our second speaker. All right. She is UC Berkeley arachnologist, Trinity Walls. Trinity is a PhD candidate studying jumping spiders with Cal Professor Damian Elias, a terrific recent Wonderfest speaker himself. Trinity earned her bachelor's degree in biology at Washington University in St. Louis, and her master's degree in biological sciences at the University of Cincinnati. I said that Trinity studies spiders that jump. As scary as that sounds, Trinity prefers to say that they dance. And I think she'll explain that they do much, much more. Please welcome UC Berkeley spider lover and Wonderfest Science Envoy, Trinity Walls.
Thank you
Okay.
for that wonderful introduction.
As people watch you get your screen ready, I want to point out your frightening and lovely earrings.
I do have a lot of spider gear, yes. Okay, so it's spider time. But before we switch just directly into talking solely about spiders, I do want to make a connection to space because we just talked about space and we have sent spiders into space. I think the first time we did it was in 1973, and we've done it a couple more times since then. But basically, we wanted to see the effects of zero gravity on animal behavior. And so we decided to do this with spiders. And we found that in the absence of gravity, spiders actually use different light cues to orient themselves and change their webs based on where the light is. So there you go. Spiders and space are connected. Okay, so I like to get a feel for people's opinions in the room before I really get started. So if people can look at their, locate their reaction buttons and find that reaction, find that raise hand button, could people tell me how many people here or have immediate family members that are either afraid of spiders or actively dislike spiders? Just show hand. Okay, awesome, wonderful. Okay, fair enough. Hopefully after this talk, you'll at least find spiders a little more interesting, necessary for the environment, and maybe a little less despicable. So again, I'm Trinity. I'm a graduate student at Berkeley, and I love spiders. Oops, my slides are not going through. Okay, but why? How did I get here? Why do I like spiders? Well, I'm actually going to start from when I was really young. So as a child, I was always into anything that crawled or moved on the ground. My mom said she noticed when I was about 2 years old, I liked beetles and all kinds of other things. By the time I was 4, she said she actually noticed that I had honed in on spiders. She couldn't figure out why, but I had. And at 6 years old, these are some of my earliest memories. Adults were always telling me that spiders were going to hurt me, bite me, attack me, chase me, all these different things. And I remember being 6 and standing on a sidewalk, watching this tiny little spider run away from me as fast as it could go, just little legs just flying as fast as it could. I remember thinking, when is it going to bite me? I don't believe you. What my eyes observe is different than the narrative that I've been given. So how do I find out what is real? How do I know? I guess I got to study it myself. So I started to do just that. And you can imagine how this went for my spider-fearing mother and the absolute mayhem I inflicted on her as a child. She was really excited to have a girl. She planned to dress me up and go shopping and do all these things. And I started off dancing. So she was excited because she thought she was going to get a little ballerina. What she got was closer to this, like a flower fairy flitting through the forest, reveling in dirt, kind of that. And along with this came all of these, basically any spider that got into my yard or my house, which I promptly adopted. And then eventually this is my first tarantula I've ever had. Her name is Anastasia. I got her when I was 16. So as I got older, I began to ask other people, why are we afraid of spiders? Why are you afraid of spiders? Where did that come from? What about spiders is scary? And I got a variety of answers. I'll just give you a few things. They have too many legs. Okay, so what is an appropriate amount of legs? No more than 4. Seems like a random number, but all right, sounds good. They have too many eyes. Have you seen a spider's eyes? No, but there's too many. Okay, but you've never seen them. They're too hairy. Pretty sure there are lots of very hairy people walking around on this earth. I'm not really sure what the problem is. And then of course they're fast, they're mean, they're deadly. And a lot of that's also just not true. The majority of spiders on the earth, especially in the US, are entirely harmless to humans. And the couple that can actually inflict any type of adverse reaction on us, generally not deadly. It's not going to feel good, but unless you're allergic to the bite, you'll be all right. You'll be all right. So where does this come from? Where do we get these fears, and how do they perpetuate? Well, some of it comes from the media. In the past, most of the news related to spiders has been negative and sensationalized, and in many cases still is today. Some of you guys may have heard of Joro spiders, which were sweeping across the southeastern US. We talked about these in 2022. They're massive, horrifying spiders falling from the sky. Are they massive? Yeah, they're pretty big, but I wouldn't call them horrifying. And they're also harmless. They're just big spiders who ended up here, and they're just making houses because that's what spiders do. Another one is because of movies. A lot of movies often depict spiders in this frightening and unrealistic manner, such as Arachnophobia and Eight-Legged Freaks. This spider that's actually in this shot that you can see here is based on Habernatus orbis, and Habernatus is the genus of spiders that we actually study in my lab. Those spiders are so tiny, they are so small. I would say you could probably fit 6 to 8 easily on your thumbnail. Like, they are very, very small, and yet somehow you end up with movies like this where they're attacking police cars. Myths is another big one. How many people have heard of the myth, we eat 6 to 8 spiders in our sleep? Anybody ever hear of this myth? I grew up with this myth. This was a thing that I believed as a child. But as I got older and learned more about spiders, I realized it doesn't actually make any sense. Spiders essentially have ears on their feet. They have hairs that function like the hairs in our ears, and these hairs essentially detect vibrations. So if spiders were to intentionally run into our open mouths while we snore and sleep at night, it'd be like running towards an earthquake or a cave with a loud predator inside. They don't normally do that. It's pretty unlikely. Another big one is medical misdiagnoses. This actually happens quite a bit, and a lot of general misinformation about spiders. So people will get bitten by something. Sometimes it can be a spider, but sometimes it's not. They're not really sure. They see 2 holes in their arm or somewhere. They go to a doctor and say, I got bitten by a spider. And sometimes those doctors will say, yeah, all right, so yeah, cool. And then they'll give you some antibiotics or medication or something. And doctors are professionals and amazing at what they do, but they're not arachnologists. Again, an arachnologist is someone who studies spiders or other arachnids, somebody like me. So they're trained to treat different things, but they're not trained to identify spiders or the bites that people have. It doesn't really work that way. So to give you an example, I actually have friends who have come to me here and said, oh, I was bitten by a brown recluse, like the spider on the screen. And I know that it's the case because I went to a doctor and they said, yeah, that's what happened. Brown recluses don't exist in the Bay Area, so I don't think that's what happened. But I don't blame the doctors for thinking that, because that's not what they're trained in. So what do we know, and how do we find out what we don't know? We do that through science and observation. So at this point, I invite you all to open your minds and embody this quote by Steve Purchell, which I absolutely love. Explore a world that until now you have only stepped on. I love that quote. And so the question is, what can spiders do? What makes them interesting and diverse? Well, obviously, based on this photo, they can be colorful and, dare I say, downright beautiful. This is a jumping spider found in Sri Lanka and India. They also can mimic other creatures. The top picture is a picture of an ant, and the bottom picture is a picture of an ant mimic spider. So spiders can mimic other animals, and sometimes they actually infiltrate their colonies. There are spiders that live among ants and essentially, well, they steal their babies and eat them, but still, the point is they live among ants and you can't even really tell. Other spiders are amazing at camouflage. Can you really see this spider very well? Can you imagine seeing a branch and seeing something like this? Would you notice it? Can you tell which part of the spider is the head and which part is the back? Can you tell where all the legs are? Kind of hard to see. To give you another perspective, it looks like this. This is the wraparound spider. These guys are located in Australia. Spiders are also incredibly necessary. They keep insect populations down. Those flies and roaches that get into our houses, spiders help with that. Some farmers have even released spiders into their fields when there are too many insects eating their crops. They're also inspiring. We have used properties of spiders and their behaviors for our own inventions. For example, in 2019, researchers at MIT were developing a double-sided surgical tape that adheres to and seals wounds incredibly quickly and absorbs water without compromising the tape's strength. They got this from the properties of spider webs. Another example, we use silk to make body armor and other types of clothing because it's flexible, more durable, and stronger than a lot of our man-made materials. This is actually a garment entirely made of silk from Madagascar. And speaking of silk, spiders also have various ways of catching their prey. Some build webs and wait for things to fly in. Others sit and wait for their food. Others actively hunt. Some are hiding in burrows and have trap doors and they spring out, grab their food. And others jump, like jumping spiders. And some people will tell me, oh, but jumping spiders are so scary. They're always jumping around. You never know where they're going to go next. And I always ask them, do you know what a jumping spider looks like when it jumps? It looks like this. It's like flying through the air with its big eyes and its legs spread out. And honestly, it misses its target a lot of the time. So when you view them in this light, at least I think they're not nearly as scary. And their jumps aren't necessarily always attacks. That's also just how they move around. So jumping spiders are some of my favorite spiders, and the rest of this presentation will mainly focus on them because that's what I study. And just jumping spiders are also very diverse. I also want to mention that jumping spiders are essentially tiny cats. So when you think of a jumping spider, think of a small cat. You can play with them, interact with them, get them to chase things, build them a little jungle gym, all kinds of things, but they're small cats. They're, again, very diverse. This is a jumping spider from Botswana. You can also find them in Nigeria, Zimbabwe, around those areas. And yeah, it just looks like this. This is not, this photo is not modified in any way, but it kind of looks like it has mascara or makeup on. One of my favorite things about jumping spiders, and this is what my lab focuses on, is their communication. So jumping spiders have complex ways of communicating and sending signals to each other. Some of these include visual signals, like waving their legs around in combination with different colors, because they can see some colors, and ornaments on their the legs or bodies. They also produce vibrations that travel through the ground. We call this substrate-borne sound. And we need to understand this for us to better understand spiders and for conservation purposes. 97% of insects also use sound that travels through the ground to communicate. So understanding how they communicate and how our actions affect their communication is important. So at this point, you're probably wondering, okay, you're showing me a visual. What does it sound like? You want to know. Well, I'm going to show you. These are peacock jumping spiders. So these guys are also found in Australia. We don't really have any like this around here, but we do have the habernatus that I mentioned earlier, like those ones in the eight-legged freaks. We have those in the lab. We have those in California. So I'm going to show you what that sounds like. I should also mention, they have kind of phases to their sound. So sometimes they'll do one thing, then another, then another. It almost sounds like a song. We call it a song and dance because they have almost like verses. So this is a video that was taken in our lab. That's a male. He's approaching a female, but I don't want him to actually touch her, so I'm going to click him away. Sounds like a cat. He gets a little angry. Starts again. No. Yeah. So they have all these crazy noises they make, which is incredible. And we have the technology now that we can actually detect these types of things. So my lab does a lot of this work. And I love these spiders. They're called paradise jumping spiders. But I actually ended up falling in love with another spider species that is much larger and actually kept as pets. So I actually fell in love with regal jumping spiders, or Phidippus regis, which are these guys right here. These gorgeous spiders are found primarily in the US and the Caribbean, and people started to keep them as pets and realized that they're actually highly visual. They're super curious. They're large for jumping spiders, so they're about inch to an inch and a half long when they're fully grown. They're unlikely to bite, and they're ridiculously cute with their little heart shapes on their butts and whatnot. The top right picture is the males. So the males are generally black and white with those green or blue, what we call chelicera, their front facial structures. And all the other pictures in this slide are females. So people are beginning to learn more and more about these guys and keep them, and they want to share this information, but it's not getting published. So I wanted to contribute to this knowledge gathering that's happening. So I decided I would study them myself. I also love them because they make excellent outreach animals. They're big and you can actually see them. So I can actually take them to schools and let them interact with kids, which is great. So just to give you kind of an example of what this looks like, this is a small one on somebody's hand. I told you those other spiders, you can get fit 6 to 8 on somebody's thumbnail. This is a thumbnail and you can see you can only fit one of these spiders on it, and it's not full grown. So I specifically study preferences. We as humans have preferences for different things. The people that we interact with, noise levels, music, food, how much time we spend working, when we work, different atmospheres, all kinds of things. And these preferences change over time as we get older and gain experience. Some of us have totally different preferences now than we did 10 or 20 years ago. And this is true of many animals as well. Those of you who have pets may have noticed that those pets may have a favorite treat or a favorite toy, a favorite spot in the house. Maybe some prefer to run around a lot. Others prefer to sit around and nap. So most of us have experienced preferences, and this is pretty common in animals as well. In fact, did you know spiders have preferences too? They do. They have preferences for different colors, age, temperature, size, sound, textures, all of it, and even more. And all these factors affect their behaviors and interactions with others. As a scientist and as a spider enthusiast, I find this fascinating. And I was really curious about how these preferences might influence whether or not regal jumping spiders decide to mate or choose a partner. So what did I do? I traveled to where they are the most abundant, which is Florida, collected a bunch, brought them back, raised them in the lab. And once they reached adulthood, I essentially gave them a stage, a camera, some lights, and said, okay, show me what you can do. This is obviously a very cartoonish depiction, but to give you a more concrete example, it looks and sounds like this. For the male's on the left, he just runs forward and says, notice me, over and over and over again. And she is paying attention, which is great. So there are lots of factors that can affect whether these spiders mate and their preferences. I'm looking at quite a few things, but I'm only going to mention a few here. I'm looking at age, the mass of the spiders, the size of the spiders, because there's definitely a lot of evidence that size of the spiders matters, how much effort the males are putting in. There are a lot of studies that show that males that put in more effort are more likely to mate, and sometimes the females will just cannibalize the males or eat the males as soon as they get in there if they're not doing enough. So all of this matters. And other studies have shown that a lot of jumping spiders in the beginning have a 30 to 60% mating rate. So they mate 30 to 60% of the time initially. So I thought, great, I have a baseline, I know what I'm doing. This is what I expect the first time. No, my spiders mate it essentially every time. They don't care about anything. So I don't know why that is. And that kind of threw a wrench in my plans because none of this matters if they mate all the time. They also don't eat each other. They just hang out together. So even if they finish mating, I will literally find them side by side. I don't know why that is, but I'm very curious. So then I was thinking, what do I do now? Oh, wait, sometimes preference changes with experience. They've got some experience now. What happens if I mate them again? So I did. And lo and behold, there's a difference. Now they only mate 45% of the time. Okay, now what are they paying attention to? If something has changed, what are they paying attention to? And I honestly haven't finished analyzing all of this yet. So far, I know they don't care about age. They don't care about mass. I don't know yet if they care about the size or length of the spiders. We're going to see. I think they might care about the effort because I'm definitely visually at least seeing some differences in effort put in by the males when they can actually detect whether a female is mated previously or not. And I think some of them are putting in a little less effort, so maybe that's why. But who's to know yet? So I'm still doing that. So what have I learned so far? Well, regal jumping spiders gain preference with experience. And we know that experience affects decisions, and this helps us understand the links between brain behavior and evolution. These decisions also influence what characteristics are passed to future generations. We know that we get many characteristics and even preferences from our parents, and the same is true of animals. So looking at these decisions affect how animals persist, adapt, and evolve. So it's really important. What do these spiders prefer? We don't know yet, and that's okay. That's the point of what And that's what science is. It's ongoing and changing and evolving. And that's just like the preferences of my spiders. Much of this information can also be applied to other animal systems. And since spiders are so readily available and beneficial, we need to study them to understand more about animal systems, their maintenance, and the factors affecting their survival. So now that we've kind of reframed our view of spiders, I want to leave you guys with some words that I personally use to describe spiders instead of the negative ones I showed in the beginning, some hidden gems, if you will. Spiders are diverse, they're beneficial, and they're beautiful. They're also charismatic, inspiring, and awesome. Honestly, spiders are misunderstood little creatures, and they really don't ask a lot. If anything, they're full of helping hands or legs, so why not give them a shot? My name is Trinity, and I'm your friendly Bay Area arachnologist. Thanks so much.
Wow. Thank you, Trinity. Oh, man. All right. I've got a couple questions, but I certainly don't take priority here. Let's see if there are any raised hands or questions in the chat. Not yet, so let me fire away. Trinity, you mentioned that you picked up a number of spiders in Florida and transported them back to the Bay Area, back to your lab at Cal. Is it easy to get a suitcase full of spiders on an airliner?
Oh, this is recorded. Yeah, yes, it is actually. It's extremely easy. You know, people are not really looking for a suitcase full of spiders when they're checking your luggage. So I've done it both in my checked baggage and in my carry-on, several hundred actually at a time. They're just not looking for them. They're sealed super well, and I usually put a note on them that says, you know, these spiders are for research and like the reasons they're there. But yeah, it's never been an issue.
All right. Yeah. Thanks, Trinity. I see Stuart has a question. Stuart, I'll read it unless you want to ask it yourself. All right, here we go. Are observed preferences unique to individual spiders, or are they common among all the spiders of a species?
Ooh, okay. So that's a two-part question. So I love it. Okay, so it can be universal in a species, depending on what it is. Maybe some species prefer certain vibratory sounds or certain leg movements. That is absolutely can be true, and we've detected that in different species. At the same time, there are a lot of studies involving personalities, so individual differences that are repeatable between spiders that are of the same species and been raised in the same way, but spider A is a little bit different than spider B for some reason. And sometimes, yes, those can be preferences. Sometimes those individual spiders have a little bit of a different preference than its neighbor. So kind of both.
Great. Thank you, Stuart. I see a question here from Samuel Fromer. How much do we know about what the spiders might be communicating with the courtship rituals? Do they communicate outside of courtship?
Oh, yes, they do. So we know a decent amount about what we think they're communicating based on a plethora of studies that have happened. So this happens in jumping spiders. This also happens in wolf spiders and some other spiders. And sometimes they're communicating how long their legs are. Sometimes they're communicating how, again, they have ornaments sometimes. So I used to work with the brush-legged wolf spider, and they have really long brushes on their legs. And it seems that they would show or wave their legs or show their brushes to the females, and then females would more readily mate with the males that had longer brushes. And we were able to see this because we actually kind of knocked the spiders out and kind of lasered off some of those hairs to see if it differed, if the hairs were shorter. And so it does differ. We've also seen that if spiders are infected and have bacteria in them, their legs are often, when they reach maturity, their legs are not nearly as long or as well developed. And females can also detect that. So females will be less likely to mate with males that have shorter legs because it can show maybe a bacterial infection or some type of health issue that she doesn't want to pass on to her offspring. There was a second part to that question. What was the second part?
Well, do they communicate outside of courtship was the second
Yes.
part. The first part was what are they communicating in the courtship rituals?
Yeah, so they're communicating fitness, strength, size, all of those different types of things they can be communicating. in their courtship rituals. And that goes both ways because males are communicating that, but they can also detect female silk, and female silk actually has a lot of, we don't exactly know how this works, but female silk, they can actually tell if females have eaten recently based on the silk, if they've mated recently, if they are mature, all of those things. We've done experiments with all of those, and they seem to be able to detect that and change their behavior accordingly. Spiders also can be competitive. So outside of courtship, two males will encounter each other and be very competitive, even if there's not a female nearby. And so they will get close together, spread their legs out, and usually the one with longer legs wins, but they'll interlock their fangs, kind of spin around in circles for a little bit, wave their legs for a while, and then the smaller one eventually loses and runs off.
Cool. Trinity, thank you. The Mannings have asked this question. What do you feed your spiders?
What do I feed my spiders? I generally feed them, so the big ones, I feed them crickets usually. The smaller ones, the little hibernatus, get fruit flies. They're too scared. They're not willing to take on anything bigger than that. In the wild, I've seen my spiders eat grasshoppers, catch dragonflies. Somebody saw one of them eating a frog. I mean, they're pretty fearless.
Also, of the two videos you showed us of, I guess, a courtship ritual, the dancing male spiders, evidently, if they don't impress the female properly, we didn't see the ending, luckily, in your videos, the female may eat the male?
My spiders, but in the smaller ones, yes. The females, that happens pretty frequently. Sometimes if the male just doesn't court fast enough, he lands on the ground or near the female, she doesn't realize that he's her species and will just grab him immediately. He doesn't even get a chance to court, so he needs to court as fast as possible. Wow. Because she'll just eat him immediately.
Thank you. We have a last question here from Kramer, a terrific Wondernaut. She says, I love spiders coming in and love them even more now. Can spiders that we find inside survive outside as well?
It's a question because this is something that I learned later in life, but so some of them that come inside, like wolf spiders and other things, they didn't really mean to be inside. Maybe it's because of the weather or because of water rising or something, but like those ones can survive outside. A lot of the spiders though, like some of the house spiders you see, no, they will not actually survive outside. They were born in your house. They need to stay in your house. They're not used to the predators and other things outside. They're used to being in that one corner, and they may move from one corner to another, but that's about it. So yeah, a lot of the house spiders in your house, they will not survive outside, but wolf spiders and other ones that are just wandering through, they would be fine.
So Kramer, good question. Painful answer. I guess this means that if you and I find spiders in our respective homes, we got to keep them there.
Yeah.
Escorting them outside will not do them much good, apparently. All right. Trinity Walls, thank you very much. I want to thank everyone here. Remember that our next Wonderfest and Berkeley Public Library collaboration happens on Monday evening, March 27th. It's Ask a Science Envoy, Biodiversity, and Cosmic Maps. Please visit wonderfest.org for more info. I end tonight by thanking all of you Wondernauts and friends of the Berkeley Public Library, especially to Wonderfest supporters and patrons. And third, of course, to our wonderful Wonderfest Science Envoys. Please give a big final, perhaps American Sign Language silent applause to our envoys, Trinity Walls and Joe Singh. Hey, thank you all for being here, and I hope to see you at our next event.